Okay, so last lecture we have talked about the cyclic groups, and then we have started with the properties, and we started with the examples. We have given some examples of the cyclic groups, simple ones, and the definition was if G have an element A which generates the entire group, then G is cyclic. And then there was this theorem which says that G be a group and there is an element in G, A. If A has finite infinite order, then A power I is equal to A power J if and only if I is J. But if A has finite order, say N, then A power N should be E. Then the set which is generated by A is going to be this one, and A power I is equals to A power J if and only if N divides the I minus J. Now we prove this theorem, and we say that the corollary is this one. For any group element A, order of A is given by the order of set generated by A. And there was this another corollary where we said that G be a group and A be an element of order N in G, then A power K is equals to E. Then N divides K. And then there was this relationship between the order of the product of AB and the product of order of A and order of B and their products. So we said that if A and B belong to a finite group and AB is equals to BA, then the group is abelian. Then the order of the product AB will divide the order of the products of orders. And we have also proved that. Now, first we will talk about the importance about this theorem 4.1, which is that in finite case, it says that multiplication in the set, which is generated by A, is essentially done by addition modulo n, which you can check. It is indeed like that. That is, well, if you add I plus j and mod n, that is going to be k. So you can actually say that a power I multiply a power j is nothing but a power k. And there you can use the Euclidean algorithm to show that. And thus, no matter what group is or how the element A is chosen, multiplication in the set A in the set generated by A works the same as addition in Zn whenever the order of A is n. And that is true. And that is why the theorem is important. Now we will prove the theorem. We'll present the theorem 4.2, which roughly says that the set generated by A power k is given by A power GCD of n and k, and the order of A power k is given by n quotient GCD of nk. And this is very interesting. So the statement will be, let A be an element of order n order n in a group, and let k be a positive integer, then the state generated by a power k is going to be the state generated by GCD of nk, a power GCD of nk, and the order of a power k is given by n quotient GCD of nk. Now we will prove this. Now to prove this theorem, what we need to do is that we simplify the notation first. So to simplify notation, let d is equals to GCD of n comma k, and let k is equals to d into r, right? Now since a power k is equals to a power d power r, we have by closure that closure that state generated by a power k should be always inside the state generated by a power d. Remember, d is the GCD of nk. Now by theorem, by the GCD theorem, by GCD theorem, by GCD, by the definition of GCD, you can say, not, let's not mention that by definition of GCD, there are integers s and t such that d is going to be ns plus at, and this is mentioned in a course which I have done on the Introduction to Pure Mathematics. So if you want to know about this, how we can write this, you can find a lecture in that one. Okay. So a power d is going to be a power ns plus at is equals to a power ns into a power kt, and this can be written as uh, let's write, let's take this part and put it here, so we can, now I can write that this is nothing but a power n power s and a power k power t. Now I know that order of a is n, so this is going to be e, into a power k into t, and this I can say is going to be only a power k power t, and this surely lies inside the set a power k. Okay, this proves that a power d is subset inside a power k. So we verified, first thing is verified. Okay, perfect. So that we can write that. So we have verified that a power k is equal to a power GCD of nk. Okay, perfect. Then we prove the second part of the theorem by showing first that showing first that order of a power d is equal to n over n quotient d for any divisor d of n, right? Now clearly a power d power n quotient d is going to be a power n, which is e, so that a power d, order of a power d, is less than or equal to n quotient d. On the other hand, if I is a positive integer less than n quotient d, then a power d power I is going to be not equal to e. By definition of the order of a. So we now apply this fact. With d is equals to GCD of n k to obtain that order of a power k is going to be equal to order of set generated by a power k, and this is equal to order of a power GCD of n comma k, set generated by order of a power GCD of n comma k, and this is nothing but order of a power GCD of n comma k, and that we have shown in previous theorems. And I should also pick up this line. It's gonna work. And this is equal to n quotient GCD of n comma, because n is going to divide. So this GCD of is going to divide n. This is coming from the previous theorem. Okay, so this is the proof. Now, by doing the simple arithmetic, the next two examples illustrates how theorem 4.2 allow us to easily list the elements of cyclic groups and compute the orders of elements of a cyclic group in cases where the elements are inconvenient to work with. So let's try that. Example 5. Example 5 says, for order of A is equals to 30. Okay, we find that the set generated by A power 26, set generated by A power 17, A power 18, and order of A power 26, A power 17, and order of A power 18 . So since GCD of 30 comma 26 is 2, so we have order of the set generated by 26 is nothing but the set generated by A square, and that is going to be E A square A power 4 up to A power 28 . A power 28 . And order of A power 26 is equal to order of A square, which is nothing but 30 over 2, which is equal to 15. Similarly, since the GCD of 30 comma 17 is 1, so we have A power 17, the set generated by A power 17 is going to be generated by A power 1, and that is E A A square A cube A power 29. Okay, and order of A power 17 is equal to order of a power 1, that is going to be 30 over 1, which is equal to 30. Okay. Now, since again GCD of 30 into 8 comma 18 is going to be equal to 6, we have say generated by a power 18 is equal to say generated by a power 6, and that is going to be e to power 6, a power 12, a power 18, a power 24, and so on. And the order of a power 18 is equal to order of a power 6, which is nothing but 30 over 6, which is 5. Okay, and this is how the theorem 4.2 help us understand and find the orders and the sets for the higher powers. Now, we can also go for more higher powers, and let's say we have example 6, which says that for order of a is equals to 1000, we find order of a power 185, sorry, the set generated by a power 185, 400, 62, and the orders of these sets the orders of these sets okay, same method, since GCD of 1000 and 185 is n calculation, you can, okay, let's try to do that for 1 and 2 power 3 5 square comma 2 square 5 into 17, and this is going to be 2 square into 5, 5, that is going to be 20. We have we have set generated by a power 185 is equal to the set generated by a power 20, and that will have e to the power 20, a power 40, a power 60, up to a power 980, and the order of a power 185 is going to be order of a power 20, and that is going to be 1000 divided by 20, and that is going to be 50. Okay, and I'll leave rest of the other for you to do that. Now I'll talk about the corollary. So corollary 1 says of this theorem that orders of elements in finite cyclic groups. Okay, this corollary 1 talks about this. So statement is in a finite cyclic group, the order of an element divides the order of the group. And this is very, very important thing and very important and very useful thing to understand and work with. We'll see about this in next few chapters or even in this chapter. So corollary 2 is about the criterion for a power I is equals to a power state generated by a power I is equals to a power j and their orders to be equal. Okay, the statement is going to be, we say that let order of A is n, then the set generated by a power I is equals to the set generated by a power j if and only if the GCD of ni is equals to the GCD of nj, pretty clear by the theorem, and the orders of a power I is equals to order of a power j if and only if GCD of ni is equal to GCD of nj. Okay, and we can actually prove this corollary. Proof is theorem 4.2 states or shows that a power I, say generated by a power I, is equal to the say generated by GCD of ni, and similarly say generated by power j is equal to the say generated by power GCD of nj, so that the proof reduces to proving that proving that A power GCD of Ni is equal to the set generated by GCD of Nj. It is only equal if their GCDs are same. Now certainly GCD of Ni is equal to the GCD of Nj implies that the sets are equal. The sets generated by these powers are equal. A power GCD of Ni is equal to the set generated by A power GCD of Nj. So, on the other hand, set generated by A power GCD of Ni is equal to the set generated by GCD of Nj implies that actually their orders are same. Their orders are same. So that by second conclusion of the theorem 4.2, so that by second conclusion of theorem 4.2, we have n quotient GCD of Ni is equal to n quotient GCD of Nj, and therefore these GCDs are same. If GCDs are same, then everything is equal. Okay, perfect. This is corollary 2. Now the corollary 3 says that generators of finite cyclic groups talks about generators of finite cyclic groups. The statement is let order of A is n. Then the set generated by A is equals to the set generated by A power I or A power j if and only if GCD of Nj is 1. GCD of Nj is 1, and we have seen this in the example, and order of A is equal to order of A power j if and only if GCD of Nj j is 1. Okay, perfect. And last corollary of this is going to be corollary 4, which talks about the generators of Zn. The statement is an integer k of an integer k in Zn, and Zn is a generator of Zn if and only if and only if GCD of n comma k is 1. And these are all the important kind of things which theorem 4.2 gives. Now, the value of corollary 3 is that once one generator of cyclic group has been found, all the generators of cyclic group can easily be determined. For example, the subgroup of all rotations in D6 clearly one generator is itself D6, and since order of R60 and clearly one generator is R60, and since order of R60 is 6, we see by corollary 3 that only other generator is R power R60 power 5, which is R300. Now, to understand the power of corollary 3, let us illustrate the real power by finding all the generators of cyclic group U of third, U of 50. In an example, it says that find all generators of U of 50. Okay. First note that the direct computation shows that order of U of 50 is 20, and that 3 is one of its generators, and 3 is one of its generators. Okay. Now, thus in the view of corollary 3, the complete list of generators for U of 50 is, we check what? We check that 3 mod 50 is what? 3 cube mod 50 is 27. 3 power 7 mod 50 is 37. 3 power 9 mod 50 is 33. Now, We move here, 3 power 11 mod 50 is 47. 3 power 13 mod 50 is 23. Similarly, 3 power 17 gives 13. 3 power 7, 3 power 19 gives 17. Okay. Now, additionally, we had to do some arithmetic here, but it certainly entailed much less work than finding all the generators by simply determining the orders of each element of U50 one by one. Okay, so the reader or the one who is watching this should keep in mind that theorem 4.2 and its corollaries apply to only to elements of finite order. So you had to find one generator, and then all you need to do is this calculation to find all the generators. So 3 can generate 27, 37, 33, 47, 23, 13, 17. All these can generate U50. Okay, and there we will end this lecture. Thank you so much.